Hello, my name is Dogeun Kim from the IDAS lab at Seoul National University. Today, I'll be presenting on RoFormer, the transformer model that incorporates rotary position embedding. In this seminar, I will first review various approaches to handling position information transformer, discuss the limitation on conventional method, and then explain how rotary position embedding addresses these challenges. The presentation ordered it into 5 parts. First, I will briefly summarize the key points of the research. Then, to provide the necessary background, I will review related work focusing on two main approaches, which are absolute position embedding and relative position embedding. Next, I will explain the mathematical idea and intuitions on rotary position embedding. Finally, I will share the experiment's evaluation results to demonstrate how much the model's performance has been improved. Here is overall summary. This method introduced explicit relative position dependency into the query key inner product process, thereby addressing the limited on conventional position embedding method. With this approach, tokens that are close to each other and rotated by similar angle, while tokens that are far apart are rotated with large angle difference. In this way, tokens are encoding usually related position information. Next, I will explain the token embedding method that have been proposed so far. They can be broadly divided into absolute positional encoding and relative position encoding. Let us first look at an absolute position embedding. In the original version of transformer, positional information was incorporated simply by adding into the word embedding en. For example, the vector corresponding to each position was added to the word embedding. This approach is simple to implement and works to some extent, but it has a major drawback. It does not capture the structural relationship of sentence, significantly the relative distance between the two words. As a result, while it is better than having no notion of ordering at all, it is still suffer from a critical limitation. There are two main ways to construct positional information vector. The first is to make use of relationship between cosine and sine functions. In this method, the vector is constructed so that value vary both across adjacency tokens and within different positions inside a single vector. By leveraging the cosine-sine relationship, the model can implicitly infer relative position information. However, this approach has limitations. It struggles to generalize correctly to sequence lengths that were not observed during training. The second approach is to make the position information vector themselves learnable. However, this method has a drawback. It imposes a restriction on the maximum input length. In summary, the two main issues are as follows. If we make the position vector learnable parameter, the maximum sequence length becomes restricted. If we use the sinusoid format, performance degrades for long context which lengths not seen during training. That said, the sinusoid method has a useful property of being able to implicitly handle infinite length problem, and this idea is later utilized in relative position encoding. Next, I will explain relative position embedding. To overcome the limitation of previous method, Shaw proposed a new approach. Instead of simply adding positional information as an embedded stage, they incorporate it directly into self-attention operation. In other words, the calculation of the attention score between a query and a key explicitly reflects their relative position. As shown in the figure, the positional information of the query itself disappears, and instead, the relative distance between the query and key is encoded into the key. This allows the model to better capture actual distance and order difference between the words. In terms of the formula, Shaw defined the relative position vector as learnable parameter. They also use clipping to address the problem of having a restricted maximum sequence length. However, since the sinusoid form was removed, it is unclear whether this method can still implicitly handle infinite length sequence. The key contribution of this approach is the argument that it is more reasonable to incorporate positional information within the self-attention mechanism itself, rather than embedding it only at the initial embedding stage. Subsequently, Dai proposed a more advanced method with Transformer XL. Transformer accelerators from absolute position embedding, but mathematically transforms them to implement attention based on the relative position. Let us now take a look at how absolute positional embedding are implemented in the formula form. Equation 1 and 2 represent the implementation of inserting position information using the absolute positional encoding method. When applying to the attention calculation, the information is expressed as shown in equation 6. Let us take a closer look at how this is implemented. By inserting equation 2 into equation 1 and then carrying out the attention calculation, we obtain the result shown in equation 6. In equation 6, Transformer XL replaces absolute positional information with relative positional information. First, as shown in equation 1, the absolute position of the key is replaced with a relative position. Then, in equation 2, the absolute position of the query is substituted with fixed vector u and v. In this process, the position information of the query itself disappears. Finally, the weight applied to the key for the relative position is defined as a learnable parameter and trended accordingly. When comparing the two approaches described easily, Shaw's method omitted too many parameters, which make it difficult to achieve high performance. Subsequent studies have proposed various methods for relative position embedding by modifying or combining the approaches of Shaw and Transformer XL. For example, the T5 paper redefined the parameter introduced by Shaw as bias and made them learnable. While the implementation differed, the core insight is shared. Reflecting relative position difference is more efficiency than using absolute positional values. This is because when a model learns semantic relationship between the words, the distance information between them is far more useful. Now, let me move on explaining rotary position embedding in detail. The author required that the inner product of query and key to be formulated by a rotation function which take only word embedding and their relative position as input variable. Their goal is to find an equivalent encoding mechanism to solve functions which conform the aforementioned relation. Rotary position embedding does not simply add or multiply the query and key vector. Instead, it transforms them by rotating them into complex plane. Each position is assigned a different rotation angle, so the final inner product between a query and key depends on the difference between their position. The two equations in equation 12 represent this rotation in the complex plane, which can equivalently be viewed as applying a rotation matrix as shown in matrix 13. I will explain this process in more detail in the next slide. When a vector is rotated by an angle of m theta in the complex plane, it can be represented as shown by the first red line. Mathematically, this results in new condition x prime and y prime, which are expressed as follows. If we rewrite x prime and y prime in terms of matrix multiplication, we obtain the second red equation which is known as rotation matrix. Earlier, I explained the case in two dimensions, but in practice, embedding vectors are d-dimensional. Therefore, the author divides the d dimensions into pairs and apply a rotation matrix to each pair. However, M represents the index of the token, while theta varies across embedding dimensions, so the difference can also be captured within the token itself. By applying rotation to the query and key at each token position and then perform attention, the computation is expressed at equation 15. Since this equation is based on the rotation matrix, it is equivalent to equation 12 and thus achieves the intended goal described earlier. As a result, the inner products of the query and key can be formulated by a rotation function, which takes only the word embedding and their relative position as input variables. In the end, the method derives an equation based solely on relative position using the rotation function without requiring any additional training. This approach has three major advantages. First, there is no training involved. Since embedding are interpreted as rotation in the complex plane rather than being learned, the method is both intuitive and scalable. Second, relative positional information is naturally embedded. The inner product of queries and keys directly reflect relative distance without need for ad hoc technique. Third, it can be seamlessly applied to the existing transformer architecture, making implementation straightforward. Finally, the overall process can be illustrated as follows. First, the query and key are constructed using embedding tokens. Next, rotation matrix corresponding to each token's position is applied. Then attention is computed using the rotated query and keys. Another interesting property of rotary position embedding is long-term decay. As the distance between tokens increases, the inner product value gradually decreases. This prevents the model from forming unnecessarily strong connections with very distant tokens. Instead, only meaningful long-range dependencies are preserved, enabling both effective and stable learning. This property is especially useful when processing long text such as news articles or academic papers, where the context may be far away but still contain curious connections that the model should not miss. Rotary position embedding also offers advantages in terms of computation efficiency. By leveraging the sparse structure of the rotation matrix multiplication can be simplified and implemented efficiently, making it easy to integrate into existing transformer model without added overhead. In other words, rotary position embedding improved performance without significantly increasing computation cost, which makes it particularly well suited for use in large-scale language models. RoFormer have been evaluated on various benchmarks. For example, in the WMT 2014 English to German translation test, it achieved higher BLEU scores compared to both the original Transformer and Transformer XL. This improvement can be attributed to rotary position embedding's ability to better capture relative distance information between words during translation. The advantage becomes even more pronounced as sentence length increases. Next, experiments were conducted on multiple glue tasks. In these experiments, the sinusoid absolute position encoding in BERT was replaced with rotary position embedding, and the model was pre-trained and evaluated. The research shows that rotary position embedding achieves better performance on certain tasks compared to the original setup. Another experiment was conducted on CAIL 2019 SCM, a legal text similarity task. This task involves comparing loan sentences to determine how similar they are. RoFormer outperformed the previous method, showing more stable and higher accuracy. This research demonstrated that rotary position embedding is effective at capturing information relative relationship even in long context. In summary, rotary position embedding overcomes the limitations on conventional positional embedding methods by incorporating relative position information into the correct key inner products through rotation. It is simple to implement, maintains computation efficiency, and has been shown through various experiments to improve performance. Thank you for your attention.